For today's notes, you will need in-class 50. We are starting standard 12 today, and we're going to investigate a special right triangle that has 45 degree, 45 degree, and 90 degree angles. So if we look at these triangles that are listed here, we see the 90 degree angle. We don't see the two 45s, but these are 45, 45, 90 triangles in disguise. We can tell that because they're isosceles. If those two sides match, then it's going to force those angles that are opposite those sides to be equal. So the remaining 90 degrees that we have for that triangle, so that the angle sum can be 180, will get split in half. 90 divided by 2 gives us 45 degrees for that acute angle and 45 degrees for that one. So we can use our Pythagorean theorem from standard 11 to figure out what the length of this side is. That's going to be the side that's across from the right angle, which we would call C, the hypotenuse. So we can do a quick Pythagorean theorem calculation. C squared equals A squared plus B squared, which means X squared is going to equal 9 plus 9, 18. And then we'll use our same strategies that we used in standard 11 to simplify roots. So whether you were a perfect square person or a factor tree person or a factor table person, you'll show whatever work you need to get that root to be simplified. I'm just going to write the work as perfect squares because I don't have a lot of space. And so that x would turn out to be 3 root 2. So if the sides are both 3, this hypotenuse turned out to be 3 root 2. All right, let's do that again. Over here in this triangle, we're in the same situation. A right angle and then isosceles means we've got 45 degree angles in the corners. The side across from that right angle is going to be the hypotenuse. So we're going to have another C squared equals A squared plus B squared equation where X squared is equal to 25 plus 25 this time. We'll square root both sides. Again, you're going to show your work for simplifying that radical. So I'm going to use the perfect square method one more time. 50 is 25 times 2. The square root of 25 is 5, and then the root 2 stays. So when the sides are 5 and 5, that hypotenuse is 5 root 2. Now what we're hoping you're noticing is a pattern between these sides. When we're dealing with this special 45, 45, 90 right triangle, we have a very distinct pattern that's happening. The two sides that are legs always match, and then the hypotenuse across from that right angle is always going to be whatever that is, but multiplied by a root 2. Now, different teachers will fill this in different ways. So some teachers use the variable x, some teachers use the variable m. It doesn't really matter what variable you use, but I try to pick a variable that's going to avoid confusion because we will have problems that sometimes ask you to solve for x or ask you to solve for m. And so my goal is always to make sure that whatever we're writing to demonstrate this pattern is going to be something that won't get confused with a problem later on. So because of that, I'm going to call these what they are. These are both legs. That's the terminology that we give to the sides connected to the right angle. And then this is the hypotenuse. And then I'm going to use an abbreviation that we won't ever see in a problem. So I'm going to call this leg a cursive L, which means this leg is also equal to cursive L. Remember, if this is a 45, 45, 90, those two legs will match because of the isosceles characteristics. And then our hypotenuse will always be that cursive L multiplied by a root 2. So we really have two relationships in this triangle. The two legs are equal, L equals L, and then the hypotenuse is equal to L, a leg, times root 2. We're going to summarize this down here. So this special right triangle, this 45, 45, 90 triangle, is an isosceles right triangle. So if you see either the 45 degree and the 90 degree indicators or an isosceles right triangle, we know that we're going to be able to use this relationship now to solve for the sides. The sides are always going to follow the pattern L, L, and then L times root 2 for the leg, and the hypotenuse. Okay. Because we have this root 2 multiplication business going on, there are a couple of foundational algebra-related skills that we need to make sure you're good at that all involve root 2's in some way. So first, let's make sure we understand how to multiply something by a root 2. If there's already a root 2 sitting there, this is like root 2 squared. We worked on that in standard 12 or 11 as well. When you square a root or multiply it by itself, it just becomes that number underneath the root. And so if we're doing 6 root 2 times root 2, the solution will just be 6 times 2, or 12. If, however, we're multiplying a number times a root 2 and there aren't roots that match, the roots multiply together. So this 3 out front, the coefficient won't change, but root 3 times root 2 becomes root 6. Now, when we create a new root, we should try to simplify it. So if we were to imagine maybe like a factor tree approach on this one, we could split it to be 3 and 2. Those are both primes, so they can't be split anymore. Nothing matches, so that means that we can't simplify farther. But in other cases, maybe we'll end up like with a root 12 under there, and then we'll have to work on simplifying that some more. All right, moving to number 3. That one's really similar to number 2. That 11 coefficient will get multiplied by a 2 from when we multiply these roots together. So our final answer here will just be 22. And this one is actually an example of what I was talking about where simplifying is going to be able to happen. 5 as a coefficient will get multiplied by root 20. Root 10 times root 2 is root 20. But then when we think about root 20, whether we're doing factor trees or tables or perfect square method, there is going to be a way to simplify that. If I write it as perfect squares, it would be 4 times 5. So this 5 out front is going to get multiplied by an additional term, additional factor of 2 based on that perfect square simplifying or based on finding a set of matching 2's in your factor tree. And then this 5 stays inside that root. Sorry, that equal sign didn't belong there. And our final official answer then multiplies these two coefficients together and leaves that 5 inside the root. So 10 root 5. All right, the remaining problems are all equations that we might have to solve. So if we're trying to solve an equation that looks like this, x root 2 equals 7 root 2, you might just say, well, x is 7. You're right. You can kind of tell what that's equal to by inspection, by just looking at it and knowing. But the official algebraic way of solving that is that this is multiplication. So to isolate that x, we divide on both sides by root 2. Those factors simplify to be 1. So 1x is equal to 7 times 1, which is just 7. But if you can tell by looking at that x is equal to 7, that's certainly fine. When we get to this next one, we don't get quite as lucky. If I were, I'm going to switch over to pencil for just a second. If I were to try to divide by root 2, I can't divide 10 by a root. Just like I didn't multiply this 3 by the root 2. It was just the root part that was multiplied together. So this gives us a little bit of a problem. And there are 2 ways to handle this problem. So some of your teachers might divide, which gets rid of this, and then they're going to go through a process called rationalizing the denominator, where they take this root 2 that's stuck in the bottom, and they write it 2 more times in a fraction that's equal to 1. And so what that does is it gives us just the x on this side, because those cancel, and then it creates 10 root 2 over 2, which then can be simplified. So if they explain it that way and that makes sense to you, that's certainly fine. Again, those root 2's would go away. So we would have x on the left side, 10 root 2 over 2, and then 10 divided by 2 really becomes a 5. So your official answer would be 5 root 2. Now to me, that method gets a little bit confusing for some people. So another alternative that I'm going to show you to see if you like it better is that if dividing by root 2 doesn't work, we can kind of fake the equation out, and instead we can actually multiply. So I'm just copying what was already here, but I need to give myself some space. We're going to multiply by an extra root 2 on both sides. Now that seems kind of weird, but what that does is it creates a coefficient on this side when you multiply these two things together that's just a regular 2. And we just have the 10 times the root 2 over on the other side sitting there ready and waiting. So then instead of dividing by a root, we get to divide by a regular 2, which means x is equal to, if we divide this by regular 2, we get a 5, and then the root 2. So it doesn't matter which way you simplify, you just need to get really good at being able to divide by root 2 in all kinds of cases. All right, let's look at number 7. Is it going to be possible to divide both sides of this equation by root 2? Over here, they would simplify to be 1, so we'd have 1x. And over here, there's a root 6 available that we can divide by root 2. So that 17 coefficient won't change, but root 6 divided by root 2 is just root 3. So kind of like number 5, the division in that case is pretty simple. If we look at this one, we're not going to be that lucky. I can't divide a 9 easily by root 2. So I either go through the process of rationalizing the denominator by multiplying by an extra root 2 over root 2, or I remember that I can leave myself some space and multiply by an extra root 2 instead to combine these roots together and change them into a regular 2x equals 9 root 2. And divide both sides by 2, and in this case, 9 over 2 doesn't really simplify. I suppose we could write 4.5, but we don't need to. So we can just leave this as 9 root 2 over 2. So sometimes our answers, to keep them in exact simplified form, won't really look super beautiful. That probably looks weird to you, but that's a nice simplified answer for what x is equal to. All right, let's continue on and see how we'll use these foundational skills as we start applying the special right triangle rules that we learned up above about the legs matching and then the hypotenuse being L times root 2. All right, in this picture, these two sides right here are the legs. So this is equal to L and this is equal to L. This side over here is the hypotenuse, so this is equal to L root 2. If I look at this side, I can tell already that L is equal to 3. So that means anywhere else there's an L, I can plug that number in. So that tells me on this side of the picture that 3 is equal to n, and I'm done solving for n. And then on this side of the picture, m is going to be equal to 3 root 2, and I'm done solving for m. Moving on to number 2, I think something similar is going to happen. Here are the legs, so these are both equal to L. This one over here is the hypotenuse, so this is equal to L root 2. I can see right here that 7 is equal to L, so anywhere there's an L, I can plug in a 7. 7 is equal to n, we're done solving for that side, and then m is equal to 7 root 2, and we're done solving for that side. All right, let's move on to number 3 and see if it gets more complicated. Here are the two legs forming that right angle. So these are both equal to L. And then this one right here is across from the right angle, so that one's equal to L root 2. I can tell right here what L is equal to. Well, this is a little bit strange, but that 2 root 2 is going to replace both of those L's. So B is equal to 2 root 2. We're done solving for B. A is equal to 2 root 2, replacing the L, but then there's an extra root 2 that's multiplying by that L. So this requires some simplifying. Those 2 root 2's multiplied together to be a 2. There's lots of 2's in this problem. So we've got our coefficient, and then we have these 2 roots combining to make a 2. So A is actually officially 4 when we get done simplifying that expression. Continuing on again, we've got our triangle legs right here and right here connected to that right angle. So these are both equal to L. Across from that right angle is equal to L root 2. I can tell right here what my L is equal to. So everywhere else I see L, I'm going to plug in a 5 root 3. That means that Y is just equal to 5 root 3. X, however, is equal to 5 root 3 with a root 2 attached. Take those roots and multiply them together. We'll get 5 root 6, and then try to simplify the root 6. Root 6 breaks down as 3 times 2, or if you try to find a perfect square factor, it doesn't exist. If you try to make a factor table, it'd just be 1 and 6 and 2 and 3, no perfect squares to be seen. So that means our answer is already simplified, and x is equal to 5 root 6. All right, let's flip the page and see if anything gets more complicated in the next set of examples. Next up, we've got number 5. So here are our legs again. Those legs are both equal to L. Across from that right angle is equal to L root 2. So right here, I can see that 5 is equal to L. That means anywhere else there is an L, I can plug in 5. 5 will be equal to n, done solving there, and m will be equal to 5 root 2, done solving there. Onward to number 6, we've got our 2 legs here and there, so these are both equal to L. Across from that right angle is equal to L root 2. This tells me that L is 7 root 3, so anywhere I see an L, I can plug that in. V is equal to 7 root 3, and we're done. U is equal to 7 root 3, but then with a root 2 attached. We're going to multiply those roots together. And we already talked about how root 6 can't be simplified anymore, so that means we're done. And U is equal to 7 root 6. All right, before you think they're all going to be the same, make sure you stay tuned in. This one's going to be a little bit different. Here's the 2 legs, so they're both equal to L. Here's our hypotenuse, so that one's equal to L times root 2. This side tells me that L is root 10, so anywhere I see an L, I can plug in a root 10. That means that n is equal to root 10, and we're done, but be careful up here. I'm actually going to have to probably move it to a different spot to work on it, but this is what I'm doing when I plug in L. It looks like root 10 times root 2. If we put those 2 roots together, I'm going to move over here so I have some extra space. M is going to equal root 20. You're going to have to try to simplify that because you created a new root that was bigger than the ones you already had on the page. So if we do the factor tree method here, just in case that's your method of choice, maybe I split it to be 4 and 5. This becomes 2 and 2, so sure enough, I've got a set of 2's and a leftover 5. Sorry, I probably shouldn't have circled that. So that means M is going to have a 2 out front from that pair, but then that leftover that doesn't have a match is going to go back to the inside. So this is the first situation where our values don't quite look like what we expect. They still follow the pattern, but because those roots simplify a little bit, we get something that looks a little bit unexpected for that hypotenuse. Let's see if that happens anymore in these examples. My 2 legs connected to the right angle are right there and right there, so these are both L's. Across from the right angle is L root 2. This tells me that anywhere I see an L, I can plug in a 6 root 2. So up top, n is equal to 6 root 2, and we're done. But down at the bottom, m is equal to 6, oops, that's a 6. 6, that looks terrible, root 2 with an extra root 2. Sorry for the extra noise, trying to find my whiteout since I wrote that terribly. Accidentally started by trying to write an L in there. Maybe my whiteout is missing. All right, well, we'll just scribble it and start again. 6 root 2 for the L, and then an extra root 2. So now these 2 root 2's are going to combine together, and remember that makes a regular 2. So m is going to equal 12. All right, a couple more here. We've got 2 legs attached to this right angle, so these are both equal to L. The one across from the right angle is equal to L root 2. L is going to be equal to 4, so anywhere I see an L, I can plug in a 4, which means U is 4, and V is 4 root 2. Those can't be simplified anymore. Last one for this page, we've got 2 legs equal to L and a hypotenuse equal to L root 2. This time around, L is equal to 3 root 6, so anywhere I see an L, I'm going to replace it with a 3 root 6. That means Y is done. X is going to look like 3 root 6 with an extra root 2 multiplied on. And that's going to be another one that we're going to need to work on a little bit, so I'm going to work on it down below. X is going to equal 3 root 12 when we put that root 6 and root 2 together. I'll do a factor table method for this one, for those of you who are factor table people. 1 and 12, not a perfect square. 2 and 6, not a perfect square. 3 and 4, perfect square. So that perfect square is going to become a 2 out front, and then 3 goes back in the root. But remember, that's just the root 12 part. So we also have this 3 that's going to be out front as well. So that's going to give us actually a 6 root 3 as our final answer for X. All right, those are all examples of what we call matched scenarios. So the information that we're given matches pretty easily with the pattern, L, L, L root 2. The remaining examples for this day's notes are not matched up quite as easily. Some of them are still technically considered matched, but then others are going to have more complicated math going along with them. So let's dive in and see what's different about these. In this one, if we look at those 2 legs connected to the hypotenuse, where our L's should be, they're both missing. We do have information about the hypotenuse. That's going to be the L root 2 side. So this is where we're actually going to need to do a little bit of solving, because to get our L figured out, we need to get rid of that root 2 that's attached to it. Now in this case, there's an easy root 2 on both sides that can be simplified. So 6 is going to turn out to be our L. And now we know what can get plugged in for all of the other L's that we see. So if this is equal to L, that means that N is equal to 6. And if M is equal to L, then that means M is equal to 6. Kind of like we're working backwards. Number 12 is similar. So in number 12, these are both the legs, but they are missing. The hypotenuse, the L root 2 side, is what we've been given. So we need to get that L figured out by dividing both sides by root 2, which over here doesn't quite cancel out the way that it did in the previous one to make a 1, but root 10 divided by root 2 can be found, root 5. And so that just means anywhere we see an L, we're going to plug in a root 5. So N is equal to root 5, and M is equal to root 5. Number 13 is going to be more complicated. Lucky number 13. Our 2 legs are still both L and both missing. Our hypotenuse is still there and equal to L root 2. However, if I try to divide both sides of this equation by root 2, that's where I'm going to get a little bit stuck. So I'm going to go through both options here just in case your teacher rationalizes the denominator, and then I'll show you how I solve it. If we divide by root 2, that's going to get the L by itself. But we're not allowed to leave a root 2 stuck in the bottom. And since this is a regular integer 4, we can't simplify. So we're going to snag that root from the denominator and write it twice, once in the numerator, once in the denominator. Then we're going to multiply straight across. So 4 root 2 for the numerator, root 2 times root 2 is regular 2 for the denominator, which means if we now simplify, L is equal to 2 root 2. So that's if your teacher rationalizes the denominator. If your teacher is like me, they're going to go back to this equation when they can't simplify it by dividing. And instead, they're going to multiply, remember, by an extra root 2. Root 2 times root 2 is 2 L's now, equal to 4 root 2. Divide both sides by a regular 2 and end up with the same answer for L. Now that we know what L is equal to, we can replace all of the L's in the problem. And so that means that U is 2 root 2 and V is 2 root 2. So a little bit more effort to figure out what those legs are equal to. That hypotenuse didn't match very well. We're going to have the same kind of situation here. So you should try to decide whether you're going to rationalize the denominator or multiply both sides by root 2. I'm going to choose to multiply both sides by root 2 just because that's the way that makes the most sense to me, but you are welcome to use either method. When we multiply 9 by root 2, it's just 9 root 2. These root 2's multiply together to give me a 2 as my coefficient for L, and then I can divide both sides by 2 to isolate that L. 9 doesn't divide by 2 very easily, so I'm just going to leave that as the L, which means anywhere we see an L, we can replace it with 9 root 2 over 2. So V is equal to 9 root 2 over 2, and U is equal to 9 root 2 over 2. Moving on to number 15, let's see if we have to do that same process again. There's the two legs that are equal to L. Here's my hypotenuse that's equal to L root 2. This time I don't have to do that process because there's a root 2 sitting there ready and waiting to be simplified away to equal 1. And L is 3. So anywhere I see an L, I can go ahead and fill in a 3, which means X equals 3 and Y equals 3. One more example for this page, and then we'll see what's left on the very last page. Thanks for hanging in there on this one. This is actually a 2-day lesson in class, so that's why this video is a little bit longer. All right. We've got the ability to divide both of these sides by root 2, so we're going to do it. That means that L is going to equal 3 root 3. Root 6 divided by root 2 is root 3. Now that we know what L is equal to, we can plug it in anywhere we see an L. So Y is 3 root 3, and X is 3 root 3. All right. Let's turn the page and tackle our last set of examples. Same process as all of the others. So here's the two legs connected to that right angle. Both of those should be labeled with an L. Across from that right angle is the hypotenuse, which is L root 2. It's looking like I can divide by root 2, no problem. So L turns out to be 7. Which means anywhere I see an L, I'm going to be able to use that 7. So X is 7 and Y is 7. Eventually, you'll do these problems enough that you'll be able to kind of understand when that work happens, and you'll be able to say, oh, the hypotenuse is 7 root 2. These two legs are just 7. Some of you might already be to that point, but others of you, I'm just going to keep showing the work because you can always figure it out as long as you know the pattern. All right, this one tells me what L is equal to, so I'm ready to just plug that L in this time. No solving necessary. Y is equal to root 6. And then for X, it's going to equal root 6 with a root 2 attached. So I'm going to go ahead and bring that down here to work on because that means X equals root 12. Root 12, I'm going to rewrite with perfect squares this time, 4 times 3. And so if I square root that 4, it would be a 2, and the root 3 would be left behind. You could also use factor tables or factor trees to simplify that one, but it does need to be simplified. It says simplest radical form or exact simplified form. on your page, so that's important. All right, number 19, we've got our two legs here, so those are both L's. Across from the right angle is our hypotenuse, so L root 2. It doesn't seem like I'm going to be able to divide by root 2, so I'm going to choose to multiply both sides by root 2, which means I've got a 5 root 2 equal to 2L. Divide both sides by 2 after that. 5 divided by 2 would give me a decimal, so I'm just going to leave that as a fraction, simplified already. And now if that's what L is equal to, we plug it in everywhere we've got an L. So y equals 5 root 2 over 2, and I don't know that I have enough space to squeeze it in here, but 5 root 2 over 2 also equals x. They'll both be equal to that 5 root 2 over 2, since they're both equal to L. All right, we're almost there. Last three. Two sides connected to the right angle are both the legs, so they're both equal to L. That means I know what L is equal to. Better label this hypotenuse as L root 2. So I can plug 5 root 2 in anywhere I see an L, which means y is just 5 root 2. Those legs match. But x is 5 root 2 with another root 2 attached. Remember, root 2 times root 2 can be simplified. So that's really 5 times 2, which means x is equal to 10. Number 21, we've got two legs here, and then a hypotenuse equal to L root 2. Telling me that L is 14, so everywhere I see an L, I can replace it with a 14. Y is then 14, and x is 14 root 2. And last but not least, one more to finish it out. The two legs are equal to L. One more time, the hypotenuse is equal to L root 2. I am able to divide both sides of that by root 2. So I find out that L is really 5 root 3. Root 6 divided by root 2 is root 3. So now everywhere I see an L, I can replace it with a 5 root 3 to tell me x and to tell me y. All right, that's it for in class 50. Thanks for being here through all of those examples. We will see you back in class.